Okay. So welcome everybody to our 12th seminar in the Algebra, Particles, and Quantum Theory seminar series. I'm pleased to introduce to you tonight's speaker, Sean Carroll. Sean is currently a research professor of physics at Caltech and a faculty member at the Santa Fe Institute. However, if I understand correctly, he's going to be moving to Baltimore this summer, where he will be taking up a new position in both the physics and philosophy departments at Johns Hopkins University. Sean's past interests and past awards are many. His current interests include foundational questions in quantum mechanics, space-time, statistical mechanics, complexity, and cosmology, as he says, with occasional dabblings elsewhere. In many respects, I feel that Sean sets an example for researchers in our field. He maintains a high level of quality in his research output while still keeping an open mind with respect to which subjects he chooses to work on. Over the years, he has entertained heretical ideas such as modified gravity in many worlds. In the last few years, Sean has run his own podcast called Mindscape, where he interviews experts on almost any intellectual endeavor one could imagine. He has a YouTube series, which I highly recommend that every aspiring physicist watch. It's called The Biggest Ideas in the Universe. Sean has written a number of popular books, including his most recent entitled Something Deeply Hidden, which is about quantum mechanics, many worlds, and the emergence of space-time. If these sound like familiar topics, indeed they should, because these are also the topics Sean will be discussing for us tonight, when he will be telling us about how he hopes to extract the universe from the wave function. Now, before we begin, I would like to emphasize that everybody who showed up here today is here to learn. And so I hope that everyone feels comfortable enough to raise their hand and ask a question throughout the talk if they have one. If you accidentally ask a silly question, it is not a big deal. You just brush yourself off and try again next time. I would especially like to encourage questions from graduate students, upper level undergraduates, and postdocs. So Sean, anytime you're ready.
All right, thanks very much. Let's see if I can do this. All right, you see the screen correctly?
Yes.
All right, good. Yeah, thanks everyone for coming. Like, it's 9 a.m. my time. I know it's evening your time, but it looks from a quick glance at the people in the audience that the audience is scattered around the world. So this is a more disparate collection of people than I expected, but I'm completely on board with the idea that you should not feel reluctant to ask questions, that we are here to learn things. And in some sense, what I'll be doing is sort of explaining the spirit of a kind of a research program rather than focusing in on the details of any one result in that research program. I mean, what my own feelings about what I'm going to talk about are both that it's probably right in some sense, but it's very, very early days, and it could be wrong in all sorts of different ways, or it could be right and we're thinking about it wrong. So there's plenty of room for help along these lines if anyone wants to join in. And the idea is to extract the universe from the wave function. What does that mean? Well, let's just go right into it, I think. Here is, I'm assuming you all know a little bit of quantum mechanics, but I'm going to start with some things that you should know very, very well, just to get us on the same page. When you're a physicist and you're taking quantum mechanics as a student, or you're doing it as a professor, there is a procedure you are taught for constructing a quantum mechanical theory. And the first step in the procedure is to construct a classical theory. Let's call that the precursor theory. So you have a classical precursor, like a particle in one dimension moving in a potential, okay? So you have a Hamiltonian for that. And then there are various different procedures that are almost equivalent to each other, not quite, but pretty close, that let you go from that classical precursor theory to a quantum mechanical theory. Probably the most simple and straightforward, the first one you're taught, is to invent wave functions. So you have phase space in your classical theory, x and p. You pick one of those, either x or p. You construct a set of complex valued functions of that. You demand that they be normalizable. And then you go back to the Hamiltonian you had in your classical theory, and you promote the other operator. So if you have psi as a function of x, you promote p here to a differential operator, and that makes it solve the canonical commutation relations. And then you have the Schrodinger equation. You have that h in your quantum theory that you inherit from your classical theory. This is all very, very standard stuff. And then you notice, or if you're John von Neumann, you notice, I guess, yeah, was it von Neumann who noticed? Yeah, that these wave functions form a vector space. They're functions, of course, but you can add them, you can scale by complex numbers. So they form what we call a Hilbert space. A Hilbert space is a complete complex normed vector space. And so if you're Dirac, we invent notation. Instead of this wave function that really tells you exactly what it's a function of, the position, we invent this abstract notion of a state, which is just a vector in some big Hilbert space. Okay, so this is the ket for psi, and that's the Hilbert space. You can add them, you can take the inner product. And so from this point of view, when someone says, what do you mean by a quantum theory? If they say, what do you mean by a classical theory? You say, well, I have a phase space and a Hamiltonian. The quantum theory has a Hilbert space and a Hamiltonian, okay? Hilbert spaces are a little bit simpler than phase space is allowed to be. Phase space is a symplectic manifold that in principle could be topologically interesting and so forth. Hilbert spaces are vector spaces and they're kind of boring. There's no features in vector spaces, but okay, once you give me the dimensionality of it, you told me everything there is. And then the Hamiltonian tells us how that wave function or that vector evolves in Hilbert space. Now, this whole procedure is a little bit sketchy if you think about it. It's sketchy for a number of reasons. One reason is that if you think that the quantum theory is what matters, then that classical precursor is not really a fundamental, well-defined thing. You can have two very different looking classical theories that give you the same quantum theory. And this is all worth a seminar on its own, but I'm hoping you can either know it or look it up. Famously, my old teacher, Sidney Coleman, showed that what is called the massive Turing model in 2 dimensions, which is a model of a fermion that has a 4-fermion interaction, is secretly the same quantum mechanical theory as what is called the Sine-Gordon theory, a single scalar field in 1+1 dimensions with a sinusoidal potential. If you want to visualize it, if you think about, there's oscillations at the bottom of the potential that look like bosons, but there are also domain walls or kinks, which in 1+1 dimension look like little fermionic particles. And in a certain limit, you can show they act exactly like these fermionic particles. And then the bound states of these fermionic particles act just like the bosons here. So if you want to say, well, given the quantum theory, what is it a quantum theory of? Is it really a theory of bosons, or is it really a theory of fermions? And the answer is no. The answer is it's a quantum mechanical theory of vectors in Hilbert space. That's what it's a theory of. There's different classical ways of getting it, but nature doesn't start with a classical theory and quantize it. Nature just is quantum from the start. At a slightly sketchier but more dramatic level, you can have the ADS-CFT correspondence, right? You can say there is a conformal field theory in flat space-time in n dimensions, and a quantum gravity theory in an anti-de Sitter asymptotic background in n+1 dimensions, and you claim that they're different classical looking theories with the same quantum theory underlying them, okay? That's a little sketchier because it's not clear quite how to define the gravity side of things all by itself. We usually hope that the CFT is the right definition, but still, you see that even asking something like how many dimensions of space are there in your theory is not well defined. That's just not how quantum mechanics works. Quantum mechanics is a story of vectors in Hilbert space. Now, for some of you in the audience, you will think I'm cheating because I say that a quantum mechanical theory is a Hilbert space and a Hamiltonian. And you're going to be asking, well, what about observables of the theory? And here is where my bias in terms of many worlds comes in. In many worlds, observables are just things that dynamically arise from the Hamiltonian. They're not things that you put in. They're not the central piece of your analysis. But there is a technicality here when Hilbert space has uncountable numbers of dimensions, okay? And the technicality is that you need to specify an algebra of observables to completely define your theory. An observable is just a self-adjoint operator on Hilbert space, a Hermitian operator in the simple cases, but self-adjoint more dramatically or more generally, and they satisfy some algebra. And this tells you how the observables relate to each other. So if you have an uncountable dimensional Hilbert space, then you can get different quantum theories apparently from the same Hilbert space, but there's some mathematical niceties there. But if the dimensionality of H is finite, then you don't need to tell me what the observables are. The observables are simply all Hermitian operators in the theory, okay? You might think, for sort of human-based reasons, that some observations are easier to do than others, but at the mathematical formal level of the quantum theory, every Hermitian operator is an observable. So in a finite dimensional theory, finite dimensional Hilbert space, I don't need to tell you what the observables are to tell you what the quantum theory is. And I will argue that it's at least plausible. This is now very sketchy, very unclear. This is one of the things I would like to firm up, but it's at least plausible that it's okay to think about the real world as being represented by a finite dimensional Hilbert space. Let me tell you a little bit about what the subtlety there is. The point is that if you do ordinary one-dimensional undergraduate quantum mechanics of particle and a potential, that's an infinite dimensional Hilbert space. And the reason why is essentially because there's an infinite number of points where the classical particle could have been. Likewise, in quantum field theory, in essentially any quantum field theory, you have an infinite dimensional Hilbert space. One way of thinking about that is in the free field limit, everything looks like a set of harmonic oscillators, and every harmonic oscillator looks like a one-dimensional particle moving in a potential. Okay, so you know there have to be an infinite dimensional Hilbert space for the QFT because every mode has an infinite dimensional Hilbert space associated with it. But if you think physically what's going on there, the reason why you have an infinite dimensional Hilbert space is because you can put as much energy as you like into each mode of the QFT. The real world is not a quantum field theory. The real world has something called gravity in it. And if you put too much energy into a mode, the whole thing collapses to make a black hole. And then you can't put any more energy into that region without making it bigger than the region you started with. And so I claim, and this is just one of the assumptions I'm going to be assuming works here, and we can talk about the niceties later. There's details here with gauge theories and so forth, but I think the natural expectation is that in the real world with gravity, regions of space are associated with finite dimensional Hilbert spaces. That's basically the Bekenstein bound of quantum gravity. There's only so many things that can happen in a region of space. Now there's some details there I'm going to gloss over once again, because what do you mean by a region of space in quantum gravity? But I think that if you look at classical branches of the wave function, you can define what you mean by that. And that's what this obscure figure at the bottom right is supposed to indicate, that you can think about this more carefully and argue that there is a sensible way of saying that regions of space in a world with gravity are associated with finite dimensional Hilbert spaces. And what that means is, yeah, please.
Just quickly, aren't you eventually going to want unitary representations of the Lorentz group?
Well, I can't always get what I want, as a famous philosopher once told me. It would be nice to have explicit, obvious routes to getting a purely Lorentz invariant theory. This is going to get in the way of doing that. But then what you need to do is ask yourself empirically, can you get very close to Lorentz invariance, but violate it a little bit? And I think the answer there is yes in this context, but that's another one of the big questions that this whole program has. But notice that
is it necessarily Lorentz invariance that needs to give?
Well, I think this argument is good. And like you say, you cannot get a faithful representation of the Lorentz group in this situation. Therefore, yes.
So you're going to get rid of so Lorentz symmetry somehow. What about getting rid of the constraint that it's be a unitary representation?
Maybe, yeah. I have not thought about that carefully. That's absolutely possible. I kind of hope that Lorentz invariance is only approximate, because that gives a potential experimental avenue to exploring the idea, but I have no strong feelings about that. Steve might have strong feelings. Steve, do you have a feeling? You're muted right now.
Yeah, he'd have to put his hand up. All right, I have to find him.
Oh, you need to unmute him. Okay, good.
Yes, I need to unmute him. I can find him. Oh, the other thing. Yeah, there we go. The other thing too, actually. So in this series, there's I don't know if they're here or not today, but Lucian Hardy and also Howard Barnum, I think, might have talked about having. I might be misremembering what they said, but in their talks, I believe they were talking about states which were not normalized. And so they might be giving up the condition that you have unitary representation. So let me unmute you here. Oh, I need to ask, so Steve Giddings needs to allow me to unmute him.
Okay.
There you go. Okay.
Okay. One comment on Lorentz invariance is it seems to me possible that you at least say if you're talking about states that correspond to asymptotically flat spacetime, you do have a representation of the Poincare group or whatever, but it doesn't, you don't have to have local Lorentz invariance necessarily in the usual fashion that we think about in, say, GR or whatever. And that is another avenue to pursue that, if you really, maybe if you're working in something like de Sitter cosmology or whatever, you don't have Lorentz invariance precisely, but there are states with asymptotically Minkowski behavior that do have an action of the Poincare group. Yeah,
I mean, I'm kind of a believer that we do have de Sitter boundary conditions. And I think that this is, I don't want to, I'm agreeing with everything that Steve just said. I think that what I would say is that there's a whole set of questions here that come from, taking things we take for granted in particle physics, where we define infinity to be a millimeter, because everything is happening at really tiny scales. And then we extend the reasoning to cosmological reaches in a way that is not quite necessarily valid. So I want to encourage people to rethink some of these issues about Hilbert space and Lorentz invariance and representations, and really try to take the cosmology and the quantum gravity aspects of it seriously without necessarily saying what the right answer is. Should I continue on? Is that good? Yeah. Okay. So again, and the philosophy of this is at every step, there's a whole bunch of unanswered questions. And so we could sit back at every step and ponder all the questions. What I'm going to do is assume an answer to every question along the way and see where that gets me. So what I'm assuming here is that locally finite dimensional Hilbert spaces are the right way of thinking about this. Normalizable states, conventional everyday quantum mechanics. And what that implies is that if we really want to recover the classical world from a given quantum mechanical theory, the information that is contained in the specification of that quantum mechanical theory is extremely meager, much more meager than we generally assume, because we are cheating generally, is the point I want to make. So what I'm saying is that a quantum mechanical theory is described by a vector in a Hilbert space that solves the Schrodinger equation, okay? Nowhere in those words are ideas like space or fields or particles or forces or any of that. We should have a way of getting those things to emerge from an appropriate Hamiltonian acting on vectors in Hilbert space. So the rules that we're imposing on ourselves are that we can start in Hilbert space with Hilbert space-like concepts, okay? Vectors and factorizations and entropy and density matrices and entanglement. And from that, the classical world that we know about with particles and forces in space are supposed to emerge. Now, this is an unfamiliar perspective. I don't think it's radical or anything, but usually you might think that when you're given the Hamiltonian, even of a quantum theory, you can just look at it and you can tell what it is. Like you can see the symbols corresponding to particles or fields or whatever. So this, for example, is a Hamiltonian. And if I gave it to you and you had taken quantum mechanics recently, you would say, ah, yes, that is a harmonic oscillator. I know what that is. But the reason why you know what that is because you've been given the Hamiltonian in a very, very special basis, the position basis. It's not the only basis. You could also recognize that if you were given it in the energy level basis, et cetera, the eigenbasis of the harmonic oscillator. But if you were given it in a random basis, you would not recognize it, right? So how did we know to give it to you in this basis? What is the principled procedure by which we could start with a Hamiltonian in an arbitrary basis and tell you, ah, yes, that is a simple harmonic oscillator? Well, if that's the program that you're trying to follow, the only information you have to work with are the eigenvalues. of the Hamiltonian. Because if I write the Hamiltonian in some generic basis, it's going to be just a mess. And there's no reason to prefer that basis over any other one. There's only one basis that is actually picked out by the Hamiltonian itself, which is the eigenbasis, right? The set of states for which they're eigenvectors of the Hamiltonian. They have eigenvalues, the energies. That set of energies is the spectrum of the Hamiltonian. And so what I'm saying is, unless you cheat and help yourself to some extra information, the specification of a quantum mechanical theory in a finite dimensional or even in a countable dimensional Hilbert space is given by the spectrum of the Hamiltonian. That's the only sort of gauge invariant information that you have to work with. So the task that we're facing is to start with some list of numbers. You can even make them positive if you want. So you're non-zero, non-negative real numbers. And from that, you look at that list of numbers and you go, oh yes, this is the real world. This right here, we've written down the standard model of particle physics plus gravity at low energies, the effective field theory of the everyday world, okay? So how do you do that? How do you go from a list of energy eigenvalues that defines the quantum theory to an emergent description from which classical physics can be said to arise? How do we do that? So, well, to think about this, let's go back to the harmonic oscillator and its position basis. Who invented that anyway? Like, why physically in the real world do we love using the position basis? Okay, part of it is because interactions are local in position, but we have to figure out what that means first. So the answer is, in large part, because we look at it. So you look at the pendulum going back and forth, or a ball on a spring, or a wave in a medium, and you see it going up and down, right? And so that's where the position basis comes from. It's what we immediately see when we make observations in the real world. And so to make that a little bit more formal, we have the quantum mechanical system we're looking at. We have an observer and we have an environment. And again, I'm sort of relying on my Everettian biases here, because the Everettian perspective is to treat everything as part of the wave function of the universe, right? So the system has a wave function, or is part of the wave function, but so is the observer, so is the environment. So the game we need to play is asking how to decompose Hilbert space so that Hilbert space, which is initially just a featureless vector space, can be thought of as broken up into system, environment, observer, etc. And what does that mean? You know, what is the criterion we use? Well, the obvious criterion is we would like macroscopic systems to behave classically, right? A single harmonic oscillator that is just, you know, a vibrating atom might be very quantum mechanical, but as long as you get it up to a big pendulum going back and forth, it looks classical. The emergence of that classical description from just a set of energy eigenvalues is a highly non-trivial operation. So how does that happen? How does just being given the Hamiltonian help us choose subsystems such that things look classical? Well, once you pick any factorization of the Hamiltonian, so you write of Hilbert space, you write Hilbert space as the tensor product of two different subsystems. That instantly gives you a decomposition of the Hamiltonian. There's part that only acts on subsystem A, part that only acts on subsystem B, and part that represents an interaction between them. So when we're looking for usefulness of a decomposition of H into HA tensor HB, it's this decomposition of the Hamiltonian that we'll be using. And then we need to think about what is it meant to say that there is classical behavior, right? And you've probably been taught Ehrenfest's theorem. Ehrenfest's theorem is half of the answer to the question, what do you mean by classical behavior? So Ehrenfest's theorem tells you that the expectation values of these operators, x and p, obey the classical equations of motion under certain circumstances. In particular, if there's a localized wave packet whose wavelengths or whose extent is small compared to the linear size over which the potential is changing in a simple non-relativistic quantum mechanics example. That's true. It's all completely very helpful. You know, the Earth going around the sun is a very classical system. You don't need to know quantum mechanics to predict the timings of the eclipses or anything like that. But you're assuming a lot also, okay? I mean, obviously you're assuming the technical assumptions that the potential is changing slowly compared to the size of the wave function. But you're also starting in a very, very special state. I mean, who says wave functions should be localized in the first place, right? We're trying to not cheat our way into this. Why are wave functions localized? Well, you know the answer to that too. If you took the wave function of the Earth and you delocalized it in this many worlds picture, what would happen instantly is decoherence, right? The environment would monitor the wave function of the Earth, and it would instantly, on any one branch, take on some classical looking value, some localized value in space. So here is the t-shirt that we saw earlier. This is Schrodinger's cat. And the point is that I put the cat in a combination of awake and asleep, because I'm a cat person. I don't like to kill the cat. But the point is that whether it's awake or asleep gives it a different physical position in space. And what that means is that these two different parts of the cat interact differently with their environment. This photon would be absorbed by the awake cat, but would not be absorbed by the asleep cat. So if you have a cat in a superposition of two different macroscopically different states interacting with an environment, it will instantly become entangled with that environment, and it will decohere, and you will have two different branches representing different classical looking realities. Okay, there's a very fun illustration of this in the case of Hyperion, which is a moon of Saturn. Zurek and other people looked at this. Hyperion is a weirdly shaped thing, so it tumbles chaotically. And you can show that its time scale for being completely unpredictable, even given just the quantum mechanical uncertainty in its orientation, is very fast. So if it weren't for decoherence, Hyperion would not look like this photograph. It would look like just a cloud of wave function, because its wave function would have a spread all over the place. In the real world, of course, it's monitored by all the photons in the solar system. So you see a specific classical thing appearing. So what this means is that there's actually two things going on when you're asking for classicality. One is that localized states remain localized, like that's just Ehrenfest's theorem, and then you'll obey the classical equations of motion. But the other is, maybe I didn't say this out loud, in the case of the Schrodinger's cat, where you have two macroscopically different states in your superposition, one fact is the two different states will interact differently with the environment right away. But the other fact is, once that happens, entanglement stops growing. So the cat all by itself in the awake state doesn't keep getting entangled. It just interacts coherently with the photons around it. I see a hand is raised, so maybe this is a good time.
Yes. Okay. So Claudio, please go ahead. Always takes 2 tries. There we go. Go ahead.
Yep.
Claudio.
Okay. So my question would be, what do you mean by localized wave functions? I mean, there are these classical theorems that show that basically you cannot, if your Hamiltonian is bounded, then you cannot be perfectly localized to begin with, right?
Not perfectly localized at all, just, a wave packet who's mostly in some area. I just mean like every undergraduate quantum mechanics textbook. I'm not trying to be tricky here. This is not a sophisticated thing.
But okay, but my question was just like, when you pose a requirement that everything that's localized has to be localized, then it's like, what do you mean by localized?
Well, then I will develop a criterion that is very quantitative for exactly that. Here we go. Let's do that. Let's develop some criteria that are a bit more quantitative here. But I want to have, the point is I have 2 criteria, right? Localized states remain localized and unentangled states remain unentangled. Again, this is when you're in a classical looking situation. It's not always supposed to be true. This is for states that begin unentangled and classical. So the question is, we would like to have some decomposition of Hilbert space into system and environment, such that the system behaves classically. So imagine this system, once we find it, will be some big classical looking thing. We want to allow for that behavior to continue. And one fact that you can show, it's not a proof, but it's a sort of hand wavy and I think convincing demonstration, is that if you have a generic Hamiltonian, this will never be true. If you have a generic Hamiltonian, localized states do not remain localized and unentangled states do not remain unentangled. There's something special about the Hamiltonian of the world, and that's completely unsurprising. The Hamiltonian of the world is very, very special. For example, it's local, right, in space. So it's special in a number of ways, but only some Hamiltonians will this work with. And then when you have a Hamiltonian that it does work with, you still need to find the right decomposition. So
Do you have
there
any,
is this, yeah.
just quick, do you have any intuition as to why nature would choose a Hamiltonian that is so specific like this over the, infinite number of other possibilities?
I have a small amount of intuition. Let me save that for the end. Remind me of it, okay?
Okay.
I mean, it's a great question, but I mean, maybe God just did it that way because is a loud answer. But look, actually, let me not gloss over this. This kind of question arises a lot in what I'm doing here, and it's exactly an example of how thinking about exactly the same problem in a slightly different way leads you to ask different questions. When you write down the Hamiltonian of a quantum field theory, and you say like integral d3x and then some operators, very few people raise their hand and say, well, why is it integral over d3x? It's a quantum field theory. That's just supposed to take that for granted, right? But here, you could have asked that question there. It just doesn't pop into your head. Here it does. And I think that's actually kind of interesting and a way to make progress thinking about this stuff. Okay, there's this old, not too old, but established discourse about which states look classical in quantum mechanics. They're called pointer states. This is assuming that you already know the factorization into system and environment, but people like Zurek have established what to do in that situation. So what happens is, that if you have something like a cat interacting with the photons, you're looking for decoherence. And the thing that you're trying to explain is when you open the box and look at the cat, you always see the cat either awake or asleep. You never see it in 1 over square root of 2 awake plus asleep. According to the formalism of quantum mechanics, I can invent an operator that will measure the wave function in the basis, awake plus asleep and awake minus asleep. But the world somehow doesn't do that. And that's what the pointer basis discussion is supposed to help you understand. That arises from the features that combine features of the system itself with features of the interaction of the system with the environment. So it really does matter what is being monitored by the environment. So given these pointer states, we can think of them as things that are being measured by pointer observables, okay? So every observable can be thought of as a choice of basis. And you're saying, what basis am I going to measure things in? So let me choose the basis that is the pointer states. So a pointer observable is just a projection operator onto all the different pointer states or a sum of projection operators. And then there's different limits that you can look at depending on the dynamics of your system. Let's look at the limit that would apply to, let's say, Schrodinger's cat, the quantum measurement limit, where the interaction Hamiltonian is what is going to be doing the work rather than the system Hamiltonian. The system Hamiltonian sort of just goes along for the ride. And then what Zurek argues, and there's, again, many more details here that I'm glossing over, but the good pointer observable QS will more or less commute with the interaction Hamiltonian. And that's a way of saying in equations, the fact that once you're in the pointer state, you don't continue to entangle with the environment. The environment just monitors you. The cat that is awake and walking around the box doesn't grow in its entanglement with the environment because it's already decohered. It's already in a state that just all the photons bounce off of it coherently or absorbed. So for a typical macroscopic system, position is the obvious pointer observable that we choose. When we look at the cat, the reason why we see it either awake or asleep is because those two different things would be in different positions. They would have different locations in configuration space. So we want to make that into a quantitative measure. So we want to measure both the localizability, which is something that is in there somewhere, we'll eventually get to it, but also the entanglement growth, which is the more subtle and less familiar thing. So again, remember the game we're playing is we're not assuming ahead of time that we know what the system and what the environment is. We're asking, given some Hamiltonian listed as a set of energy eigenvalues, can we find a decomposition into system and environment? So for each factorization, you can define a candidate pointer observable. So the pointer observables are the thing that project onto pointer states. So for a random factorization, we can do the best we can. We can say, what is the observable that you can write as some operator of that form on the system times some other operator on the environment, and say it is doing the best it can to commute with the interaction Hamiltonian. So find the candidate pointer observable that does its best to commute, that is the lowest commutator with the interaction Hamiltonian, okay? And then you can quantify that in terms of what is called the, what did we call this? The, I forget, the pointer entropy or something like that. It's just you could do it as a von Neumann entropy, but we did it as a linear entropy because it's easier to calculate when we do our numerical examples. The point being that the growth of this quantity is a dimensionless measure of how quickly the system and the environment are becoming entangled, okay? So this is a quantitative way, S double dot here, this linear entanglement growth, is a quantitative way of saying how quickly is your pointer system, your candidate pointer system, nevertheless entangling with the environment. And the other thing, to answer the earlier question about localization, your natural thing is to say, given your pointer observable, what's the variance in that pointer observable? So you have some state, you have the density matrix for the system. Is it spread out all over the place in the pointer observable, or is it just one value of the pointer observable? So this is a way of saying, is it in a pointer state, or is it a superposition of many pointer states? The problem is that that's dimensionful. So instead, we're going to define a pointer entropy as well as the entanglement entropy. And this is, again, just a very simple quantitative way, in a dimensionless way, of measuring how spread out the state is in the would-be pointer basis, okay? And so then our algorithm, which we call the quantum mereology algorithm. Mereology is the study of the relationship between wholes and parts. So we're asking, given the whole of Hilbert space, how do you decompose it in the most useful possible way? So for each possible factorization, and this is the reason why it's not very practical in the real world, you have to imagine scanning over every possible way of factorizing Hilbert space. At a computational level, that becomes very, very hard once Hilbert space is even a little bit big. But anyway, what if you have a candidate factorization, you can easily find the candidate pointer observable that has the minimal commutation, that commutes the most with the interaction Hamiltonian. So it's being interfered with the least by the interaction Hamiltonian. You start your state in what would be a pointer state, if that was the correct pointer observable. And then you look for the factorization among all these factorizations that minimizes the growth rate of what we call the Schwinger entropy. To be very, very honest, I forget why we call it the Schwinger entropy. I think that Schwinger talks about something like this in one of his lectures someday that Ashmi found. But anyway, you have two different criteria, the entanglement and the localization. You want them both to be small. So you minimize the maximum of these two entropy growth rates. And so that's the algorithm. You minimize this quantity over all possible factorizations into system and environment. And then we checked that we get the right answer for the cases where we know the right answer. So we did a little numerical truncation of two harmonic oscillators with a weak interaction between them, okay? So we know what the system is supposed to look like. It's two harmonic oscillators with a weak interaction between them. So we know what the basis is that's supposed to look good. And then we calculate this Schwinger entropy, and then we change from that basis of Hilbert space to something else, to some other factorization. And what you find is that the Schwinger entropy is much, much lower in what you think of as the correct ordinary classical decomposition. And it's very, very large in almost any other decomposition. So the upshot of this is that by minimizing this quantity, the rate of delocalization and the rate of entanglement growth, by minimizing both of those simultaneously, you essentially uniquely pick out the right way of decomposing Hilbert space into system and environment so that the system can act classically, like a cat in a box or the Earth going around the sun. And again, continuing the idea that this way of talking and asking questions leads to different kinds of questions to ask, here's a question I've wondered about for years. Why don't we live in momentum space, right? You know, the formalism of quantum mechanics treats momentum space and position space equally, or for that matter, the formalism of Hamiltonian mechanics in classical mechanics, X and P are on an equal footing. You can do canonical transformations that switch between them. But in the real world, we always find Hamiltonians that look like this, right? P squared, maybe over some dimensional factor, plus a potential. And if there's more than one P, then the interactions will be local in Q, and P just has a bunch of P squared. So you have a kinetic energy, which is just a kinetic energy. And then the position is the variable with respect to which interactions happen in interesting ways, okay? So that's a fact about the world. And here is what, and this is only tentative, we haven't really finished this yet, but here's what we noticed, that this process of decomposing Hilbert space into system and environment looking for classical behavior, well, that defines a pointer observable, Q, right? So this is the thing that is being monitored by the environment. Like in the cat in the box, it's the position of the cat that is being monitored by the environment. So then you automatically have a conjugate observable, which is P. And this is all about entanglement, right? This is, you want to have something that doesn't keep getting entangled, but then you also want something that remains localized. And so we noticed that there exists, that Q remains localized only if it obeys this property we call collimation, which amounts to the Hamiltonian looks like this. So I know that I said a bunch of things very quickly. Let me say it again. If you start with the generic Hamiltonian, okay, and a generic choice of P and Q, it's not going to look like this in any sense. But what we have found, at least anecdotally, is that in the real world process of trying to find decompositions of Hilbert space into system and environment so the system can look classical, that works when the Hamiltonian takes this form. So what we're saying is that, yeah, in classical mechanics, I could imagine any Hamiltonian I want, any function of P and Q that I want. But the classical Hamiltonians that arise as the limits of quantum Hamiltonians with a classical limit look like this. You don't get an arbitrary classical Hamiltonian from looking for quantum theories with classical limits. You get Hamiltonians that look like this. So the suggestion is that position is special because there is a difference between one conjugate variable and the other conjugate variable in the classical limits of well-defined quantum theories. I think that's like 90% confidence in that statement. We're still working on making it completely solid, but it's interesting. It's an approach to asking a question that you hadn't thought of before.
Can I ask what kinds of different systems you looked at? Like, did you look at a big scope of different systems?
We did not, because Hilbert space is big and it gets out of control very, very quickly. But we had some hand-wavy analytic arguments for this. It wasn't just numerical evidence.
Okay.
So,
and in the cases that you looked at, did you tend to find unique solutions?
Yeah, I mean, again, it's sort of suggested by this picture here, but when you have classical behavior, it's really obvious. And when in a random generic factorization, it's not anywhere close to classical. So, I mean, if I have a system and environment and a random Hamiltonian, I would expect them to, entangle up to the dimensionality of the system's Hilbert space very, very quickly. There's no reason why it shouldn't. There's a lot more ways to be entangled. It's like entropy growth, right? There's a lot more ways to be entangled than to be not entangled. So when you have a system that remains unentangled with the environment, that's very, very special. And you can usually spot it when it's there.
Thanks.
Okay. So this is all, for better or for worse, this is recovering stuff that you just assumed in undergraduate quantum mechanics, okay? And so you might or might not think that that is an interesting program to follow. But so now let's quantize gravity, which is thought to be a more obvious research program in the modern world. And what we're gonna do here is follow the similar philosophy we had before. Start with a list of energy eigenvalues and extract classical features from that. But we will also help ourselves to intuition from what we think the classical behavior really is, okay? So what we know about in the real world is that quantum field theory in space works pretty well. So we imagine there is space and time, and at every location in space, if you have a small region of space, you have some degrees of freedom that sum together in all those regions to make a quantum field. So, and again, this is something where there's plenty of mathematical subtleties here that I'm fearlessly glossing over. But in a quantum field theory, roughly speaking, Hilbert space decomposes into a set of local degrees of freedom. There's what the field does here, what the field does there, etc. All right, Steve is not going to let me get away with glossing over the subtleties.
Okay, so he has to let me unmute him. Okay, please go ahead.
Yeah, so, well, I think this is an important point. Here, if we're really doing local quantum field theory, then because of the type 3 property, we know that there is not a nice factorization into Hilbert spaces corresponding to regions, and instead we have to focus on the operator algebras, et cetera, et cetera. So, and moreover, if you try to impose a structure of factorization into Hilbert spaces associated with regions, you are probably doing some pretty severe violence to the symmetries like Lorentz invariance. So yeah, I'd like a better explanation. And in fact, I think this may be an important point for trying to understand what the actual structure should be, that one needs to respect that kind of statement more. But comment.
Yeah, so again, this is I'm not even going to disagree. I think that that's very, very possible. Since I had, the reason why I think I can get away with this, because I've already done great violence to things like the Lorentz invariance by imagining things are locally finite dimensional. And I think that once I do that, something like this is going to be very, very close to true. So I'm giving up on quantum field theory first, and I'm just sort of using inspiration from quantum field theory to figure out what to do in my very different context. And it may or may not work. I mean, this is, that's the fun. That's why we're here. That's why we get paid the big bucks.
Well, but one thing one certainly needs to do in the end, whatever the theory is, it needs to match on to local quantum field theory, sort of in the weak gravity limit, right? And so we know that to a very good approximation, we have a structure that looks like that of local quantum field theory. So I'm wondering whether you think you can get away with this and respect that comment.
Right. You'll be unsurprised to hear that I think I can get away with this, but let's see whether I do or not. I have not actually gotten away with it. I'm very happy to admit that, but I think I can. And so let's see what happens when I move forward. But again, maybe not. But there's enough issues at every step along the way that one can, in a very principled way, feel it's very, very important to maintain this or to maintain that. And I'm definitely doing violence to a lot of things that we know about in quantum field theory, especially gauge theories, and just hoping that it all works out okay in the end. And it maybe won't. But okay. I mean, let's put it this way. We know that, at least to some approximation, we can start with a lattice theory and take the continuum limit and get a quantum field theory in the right circumstances. And the lattice theories certainly have this property, right? And so that's what we're gonna try to do. So if you did assume this, if you let yourself get away with this idea, and again, it need not be exact, like you could have different, slightly non-local nearest neighbor kind of degrees of freedom also. You could generalize this, but those are next levels of analysis here. At the simplest, dumbest level of analysis, there are things going on at every point in space in a quantum field theory. You can poke the fields and they will react locally. That's what I really need to do. And in this, so again, this is a way of decomposing, factorizing Hilbert space that has a very special property, namely that the interactions between different factors are nearest neighbor interactions. You don't get direct interactions in the Hamiltonian between what happens at this point in space and what happens at that point in space. There may be, once gravity or gauge theories are there, you might have some constraints that are non-local, but your Hamiltonian is still written as an integral over d3x, right? And so what that means in this discrete setting is that once I have this factorization, I can write the Hamiltonian as a sum over things that just act on one factor at a time, plus things that act over 2 factors, 3 factors, etc. That's an infinite series. And then the computer science notion of locality is k-locality, which means this truncates at some point, right? One factor interacts with only k of its other factors. And in fact, what we want is a stronger characterization than that, because we want those factors to fit together nicely into a something that we would recognize as a kind of local lattice structure. But it turns out that just this weaker characterization of k-locality is enough to dramatically limit your Hamiltonians. And this is actually not my result. This is Collar, Pennington, and Renard a few years ago wrote a paper called Locality from the Spectrum. So they're really looking at finite dimensional Hilbert spaces. All you have is the spectrum. They know, so if you, the typical thing again to do as a physicist is you're given the Hamiltonian of some finite dimensional system, solve for its energy eigenvalues. We're trying to go the other way. We're given the energy eigenvalues, figure out how to write it as a local system. And what they find is that most Hamiltonians, again, have no local factorization. Just like we said before, most Hamiltonians have no classical limit. And when it exists, locality is mostly unique because there are fewer parameters in a local Hamiltonian than there are energy eigenvalues. So what this lets us do, I'm obviously glossing over a lot of details, but what this lets us do is, if you think that your Hamiltonian has a local factorization, that is to say, if you can decompose it in this way such that every factor interacts with neighbors and not with faraway things, then you can find it, okay? That locality is implied by structure that is hidden in the spectrum of the Hamiltonian. So that's great. So all of this non-genericness is helping us. If there were given a random Hamiltonian many ways of finding a local decomposition, we'd be in trouble. But the reality is that it's rare to find Hamiltonians with local decompositions at all. And when they exist, you can find them more or less uniquely. Good, so let's just add gravity in. How hard can it be? Well, let me say for many people in the audience, there's a very big research program with many people involved in it, talking about extracting gravity from entanglement, right? It from qubit kind of things. Almost all of this work is being done in the context of ADS-CFT. So what they mean is entanglement in the boundary theory, giving rise to geometry in the bulk theory. And this was started by people like Mark van Ramsdonk and Brian Swingle back in the day. And it's a whole important thing. I do not want to say that they're on the wrong track or anything like that. But you know, I'm a lowbrow cosmologist at heart. I don't think I would live in anti-de Sitter space. I live, if anything, in de Sitter space. But really, I live in a world where gravity is pretty weak, okay? So all of this discussion is highly holographic. You know, it really matters that you can relate an n-dimensional QFT to an n+1 dimensional gravity theory. And in turn, that relies on the fact that you're having a whole cosmological space-time at your disposal. Here in the solar system, for the Earth going around the sun, for apples falling from trees, gravity is not very holographic. It's a weak field, quantum field theory, right? You can calculate graviton emission or something like that, no problem, as an effective field theory, and it's very local. Okay, so if I'm far away from horizons, from black holes, from cosmology, etc., I should be able to just do local weak field quantum gravity and everything should be fine. So my point is that I'm not doing this. The words sound very similar. I'm extracting gravity, curved space-time from entanglement, but in a very different way than happens in ADS-CFT, in a very different limit of interest. We want to work directly in the bulk, okay? So again, we have this sort of intuition that we get from quantum field theory. And now we're not just looking at the Hamiltonian, where we said before, the Hamiltonian sort of implies locality on the basis of the interactions being local. Now we're looking at the states as well. We start by looking at the vacuum state, a traditional thing to do in quantum field theory. And what you notice, not just in the quantum field theory, but in any local theory, entanglement in the vacuum state has a very typical structure where things are highly entangled if they're nearby, like these two places. Things are not highly entangled when they're far away. Okay, so we're going to be inspired by this observation of the real world and say, well, in our way of thinking, we don't know what is meant by near or far, but we know what is meant by highly entangled or unentangled. So given some purportedly local decomposition, let's define a metric. Let's define a distance measure on the basis of saying, if things are highly entangled, we'll call them close by. And if things are not very highly entangled, we'll call them far away. And there's some math here. I'm sorry?
Can I sneak a quick question in? So in this model, would you be able to describe something like a pair of entangled particles which are still somehow far apart?
In principle, you could, but really what I'm looking at is the entanglement of the degrees of freedom that are essentially in the vacuum. I'm not looking at the entanglement of particles, okay? So whenever I have like an EPR pair or something like that, right, in the Bell state, sure, they can be as entangled as you want and they can be as far apart as you want, but they're also surrounded by a much, much larger number of states that are in the vacuum, right, or of modes, of degrees of freedom that are in the vacuum. So if I have two particles that are entangled, and I draw little 1 cubic centimeter regions around them and ask how much entanglement there is with all the degrees of freedom in that region, the particles are going to be completely irrelevant. It's really only the non-excited modes that I'm going to care about.
Thanks.
Okay. And so I'm running, I've gone slow, so I'm running low on time. So I'm going to skip over some of the math here. I promise you there's math. It's kind of fun math. So you use the same math you use to take a scan of your brain. The radon transform is a way of taking information along slices, which we take to be, surfaces in some region or surfaces like that gray surface. And basically you can relate the area that emerges in our description to the mutual information between what's inside the region and outside the region. And then you can do perturbation theory a little bit. And so let me tell you what's going to happen so you follow the logic, because I'm going to zoom over what's going to happen. What's going to happen is, what we're going to do is relate the emergent geometry that we get from this entanglement-based metric to an energy that you would naturally associate with being in the region, okay? So if you start with the vacuum state, the flat space-time state, or whatever you want to call it, and perturb it a little bit, then think about what that means. You perturb the state a little bit. If you perturb it in such a way to decrease the entropy, decrease the entanglement between the degrees of freedom here and elsewhere, you're increasing the distance between them. This is the intuitive, there's better equations, but this is the intuition behind them. So you're changing the emergent geometry, something that might have been just flat before, now you have a little dimple in it because you've removed some entanglement from that region to everywhere else. And you can characterize this, so you can characterize the change in the area with respect to the change of the entropy. And once you've done that, it's just math, okay? And this math is actually done by Ted Jacobson a while ago. This is not new to us. If you have some region that is very small and you show that the change of the area is a certain number, that you keep other things fixed, you keep the volume inside fixed, for example, that corresponds to, in the continuum limit, the Ricci curvature, the curvature scalar at that point in space. And then if you have a particular slicing of space-time, the synchronous gauge, that Ricci curvature of the three-dimensional space is proportional to the 0,0 component of the Einstein tensor. So what you have overall, at the end of the day, is that your entropy perturbation, by changing your quantum state, can be interpreted as a change in the Einstein tensor of the emergent space-time geometry. So that gives you something that is beginning to kind of look like the left-hand side of Einstein's equation. What about the right-hand side? Well, what we would want is to relate the 0,0 component of the Einstein tensor to the 0,0 component of the energy momentum tensor. I do apologize for going fast here, but it's all in the papers. Well, there's a trick that is known in this community using what is called the modular Hamiltonian. So for those of you who are not familiar with this, you do know that if you have a thermal state in quantum field theory, thermal states have density matrices that look like e to the minus h. Okay, so this is the density matrix of a system in a thermal system. It looks like e to the minus the Hamiltonian operator. Well, look, I can always just take the log of both sides, right? For any density matrix, I can always find a Hamiltonian with the property that, or I can find there is an operator with the property that if that operator had been the Hamiltonian, that density matrix would look thermal with respect to it, right? This is called the modular Hamiltonian. It's just k equals minus log rho. So I'm not saying the density matrix is thermal, but I'm saying that for any density matrix, I can define this modular Hamiltonian, and with respect to it, the state looks thermal. And then you can prove something called the entanglement first law, which is that if you start in some state, perturb it a little bit, there's a change in the entropy that is proportional to the change in that modular Hamiltonian. Interesting. Because remember, back here, we had already shown that there's a change in the Einstein tensor proportional to a change in entropy. What we wanted was a change of entropy proportional to a change of energy momentum. And now we're telling you that there's a change of entropy. When you have a change of entropy, it's proportional to a change of something called the modular Hamiltonian or the modular energy. And then what you can do is, again, take a limit where things are very small scale compared to any massive particles, and your field theory looks almost conformal. And you show that in real world known quantum field theory examples, the change in the modular Hamiltonian is exactly what you would identify as the energy density of the theory, as T00, as the 0,0 component of the energy momentum tensor. Sorry for skipping over a lot of math, but here is the finding chart. This is the second to last slide. Here is what the overall strategy is supposed to look like. We assume, for no good reason other than we want it to be true, there's some hand-wavy reasons, but this is, we start with some input, and the input is that we can define an emergent geometry on space that has the property that when you perturb the state a little bit, the change in the area of a region is proportional to the change of entropy in the region. And then you just do math. And again, this is following these papers by Jacobson. You just do math to relate the change in area to the change in the Einstein tensor. And you use quantum field theory to show the change of entropy is also proportional to the change in what looks like the energy density if you're in a well-posed quantum field theory limit in some sense. And then you also assume that there is some kind of Lorentz invariance coming in. Now, I already told you there's not Lorentz invariance coming in, but there needs to be approximate Lorentz invariance coming in, because otherwise we're not describing the real world, okay? So this is why this is full employment for the next generation of graduate students, but there have to be the right circumstances under which, in the infrared limit, things look pretty Lorentz invariant locally. And then if you have G00 proportional to T00, you have G mu nu proportional to T mu nu, which is just the weak field Einstein equation. So what we're saying is that under a reasonable set of assumptions, I think they're reasonable anyway, when you define geometry as emergent from the entanglement structure of a quantum state from a Hamiltonian that has a local decomposition, the emergent geometry in the weak field limit will naturally obey on something that looks like Einstein's equation if Lorentz invariance is also part of the story. Now, this sounds more impressive than it is, actually, because obviously we made a lot of assumptions along the way. In our most recent paper, we were very, very careful about listing all the assumptions. So if you want to disagree with all of the assumptions, you can pinpoint where it is that we cheated. But the impressive thing is not that you got Einstein's equation, because honestly, there's not that many equations you could get, right? Once you're relating energy momentum to space-time curvature, there's only a small number of choices. What's impressive is that you can see how all of these quantities are emerging out of Hilbert space and the Hamiltonian itself without anything else being put in. That's the real effort here, like to see how we can reconstruct the emergent space-time in which we live from purely quantum mechanical ideas. So this is the aspirational program, right? We start with just vectors in Hilbert space, moving under a Hamiltonian. We show how to decompose Hilbert space so that we recognize features of it. We recognize classical behavior, we recognize locality, we recognize curved space-time. All of these are, again, questions we could have asked all along, but they're suggested by this particular way of thinking about things. So I think that this way of conceptualizing how to think about quantum mechanics is leading us to interesting ways of thinking about quantum gravity. Thank you.
Wonderful. Thank you for such a great talk. Does anybody have any questions? Okay, so David Jackson, go ahead.
Okay, thanks, Carl. Thanks, Sean. Thank you for the talk. So I think I have a question. It's just to kind of clarify my understanding of this. So normally if you start with general relativity and quantum theory, you have a gravitational constant and Planck's constant and the speed of light, and the Planck scale is relevant. Because you're starting with quantum mechanics alone, you don't have a Planck scale or a gravitational constant. I'm wondering how those things emerge. Is there something interesting that happens on the Planck scale, or how does a gravitational constant emerge?
So it emerges, if you're still seeing my slides, it emerges from turning this proportionality sign into an equal something.
Right.
So this is a fundamental assumption of the whole program, is that there is a way of relating the change of entropy, right, over here to the change of area. And that is fundamentally a dimensionful parameter that needs to relate them. So that comes into the definition of the theory right from the start. Now, I don't want to overemphasize, I don't want to make you think that there really is some fundamental distance or there's some fundamental minimum length or we're living on a lattice or anything like that. This is quantum mechanical from the start. And we're asking how to decompose Hilbert space. Okay, we're not putting points in and putting degrees of freedom on there. We're starting with a big Hilbert space and we're asking how to separate it into things that look like localized regions of space. So if you did just put the world on a lattice, there's several well-known things that would follow from that, like pretty dramatic violations of Lorentz invariance that show up in dispersion relations for photons that you can actually go test. There's no reason why those particular signs of Lorentz violation need to show up in this formalization. And even more exciting, so I mean, that's just a footnote. What's exciting to me is that I can sort of see how to begin to make this compatible with the holographic ideas, okay? Because it's not really starting with a lattice. It's starting with Hilbert space and decomposing it into ways that look local under the right circumstances. But under different circumstances, that emergent locality might look very different. So I think that the huge question, one of the huge questions that needs to be addressed in this program is to how to fit in the holographic behavior where there's a horizon and gravity is important with the local weak field, with the local behavior in the weak field limit. Anyway,
Okay,
that was not your question, but I got enthusiastic talking about it. Sorry.
But the space-time that emerges is sort of as continuous?
Well, to some approximation, yeah. I mean,
Okay.
there's not an infinite number of degrees of freedom, so it's not truly continuous.
All right. Okay. Thank you very much. Thanks.
Do you get a well-defined dimension?
Yes. I mean, you assume that you do. So again, that's a very non-generic Hamiltonian, but if you have the right Hamiltonian, you will get a well-defined dimension. And we actually showed how you can do that.
Okay. All right, so Saurabh, I'm going to unmute you. Go ahead. Oh, 2 tries every time.
Okay, thank you. I have 2 questions. One regarding the description that you gave regarding the distance and how the entanglement is related. So this really seems similar to how the ADS-CFT stuff behaves, where you have some interaction that's there, which is strong when you're really in the IR region. Is this somehow motivated by the same concept? And like, again, it kind of might be related to the previous question as to the holographic interpretation about this. Like, how is there any way to relate this somehow, or is there some motivation from the holographic principle that you've used here? And the second question would be, like, in particular, I think in the previous slide, you mentioned this IR limit. Like, why did you choose this? Maybe I'd missed it, but I was just curious as to why you chose the IR limit particularly there.
Yeah, so to answer the second question first, I'm in the IR limit. I live in the infrared limit. My life is very far away from the Planck scale. So I just am trying to explain why apples fall from trees. I recognize there are other interesting questions out there, but that's what I chose to think about. To the first question, there's zero motivation here from holography. I just know that there is holography in the real world, so I am motivated to someday include it. But all of these relationships between entanglement and distance and so forth are just parts of the vacuum state of an ordinary quantum field theory or a local lattice theory. There's nothing that is intrinsically holographic about that.
Okay, okay, all right, thank you.
Steve, I think you're next.
Yeah, go ahead, Steve.
Oh, okay. Thanks. So I guess, as you know, we strongly agree with your last statement, or I strongly agree with your last statement that we should put, quantum mechanics first. So let's do that. And let's say you start with a Hilbert space. And then, as we've both been discussing, a very interesting question is what additional mathematical structure you need to begin with in addition to Hilbert space, and what emerges. And so a sort of minimal thing, and this is just a comment, a minimal thing might be a notion of subsystems, which could provide a quantum precursor of space-time and a notion of locality. But basic properties of local quantum field theory and GR, gravity as we know it, suggests that these subsystems may involve a more subtle notion than just factorization of the Hilbert space. This touches on what we were talking about earlier.
Right.
And so, we do need something like subsystems, and that needs to match on to local quantum field theory plus GR and the weak gravity limit. And there we don't have simple factorizations. So I'm just making the comment that looks important. And then, of course, once we do understand how to define some notion of subsystems, which may not be factorizations, then clearly we will need a special form of the Hamiltonian. So anyway, there's a different sort of approach to the whole set of questions, but I thought I'd just put that out there.
No, that's right. I mean, for anyone in the audience who doesn't know, Steve and his collaborators have been pursuing a program that I think is extremely interesting and important, coming at this quantum first perspective, but making some slightly different choices as to what's important first to hang on to, and then building up in a different way. So I think it's completely compatible, and one of us may be right and one of us may be on the wrong track, or we converge in some way. So my feeling is that I think that I see a path to sort of building up, like in some very real sense, and I'm not exaggerating for reasons of humility. I think what we've done is the dumbest thing to do. It's like the most naive, straightforward, don't think too hard thing to do, see how it works. And then I can see, but it's kind of like Galileo ignoring air resistance, right? Like, I know air resistance is there. I'm going to put it back in later. But I think that finding out what happens in the simplest possible circumstances is useful. And then I can imagine building in more structure to the Hilbert spaces, because I do think that ultimately we want to get black hole complementarity and ADS-CFT and stuff like that. And you're going to need to go well beyond this very naive decomposition of Hilbert space that we chose. But I think I can get intuition here and then begin to put that in rather than insisting on it from the start. It's an empirical question. We'll figure out what happens along the way.
Yeah, we may well converge, but I think there are different starting points. Yeah.
I don't know if either of you have come across this paper or not, but I was going to point out there's an earlier paper by David Cribbs and Fotini Marco Polo from 2005, and it's called Geometry from Quantum Particles. I don't know if it's something that either of you have seen before, but it's got some early ideas that seem to relate to a lot of the things that we're talking about today.
I don't know that one. Let me again say something that I feel, I know that I've read some of Fotini's papers that are in this area, on quantum graphity, for example. I think that, and
this is not the same. Yeah, this paper isn't the same as quantum graphity. It's quite different.
No, I understand,
Yeah.
but there's a thing that people do that kind of I wouldn't say worries me, but I'm skeptical of it or dubious, or I don't know, which is to start with a system and quantize it, right? To start with some kind of structure and then make a quantum theory out of it. And so if there's anything remaining at the end of the day in what I'm proposing here, it's the usefulness potentially of taking this other point of view that just you start with Hilbert space with as little structure as you can and get everything else out of it.
That's what this program is. So, so I think
Okay.
they are starting from quantum systems right from the get-go, and there's no initial notion of geometry.
Good. Now I'll have to check it out. Thanks.
Yeah. Okay. So, Torsten, go ahead.
Okay. Yeah. My question is, or I start better with a remark. The remark is about the, you never mentioned such a low, at least locally splitting of space and time, because that is why I was a little bit wondering, because it's maybe important. Otherwise, you has problem with your structures maybe, and it is known from work of Cohn and such people that if you install such a non-trivial foliation and consider the leaf space of the foliation, you get automatically interesting structures like factor 3 algebras, which are interesting in algebraic quantum field theory. So maybe it's important to introduce such a at least locally splitting of space and time. And introduce that structures. Otherwise, I don't see why you got the Lorentz invariance or the Lorentz group installed in your system. That is remark. And secondly, my question is, what did you expect later as the geometry of the space-time itself? So I'm working a little bit on exotic smoothness structures of space-time. So I'm interested in such a topology things. Did you expect that you got really non-trivial four-dimensional topologies in your approach? Oh, and by the way, the factor 3 is also interesting because later you introduce the modular Hamiltonian, and in the factor 3 there's a so-called modular tometer theory, in which you automatically get the relation which you later introduce with the log. Maybe it's important for the argumentation to have such a splitting into space and time, at least locally, to get such a foliation.
Yeah, I mean, so there were lots of questions there. Very good questions.
Oh, sorry. Okay, sorry.
I mean, some of them you know, again, there's a lot of forks along the road to doing this, and different people I know from experience are going to have very strong feelings about taking one fork or the other. I'm a pluralist about these things. Take all the forks. So I'm not going to try to justify why we made the choices we did, but I can try to explain the choices that we did. So there's a major choice that comes in right here with this equation. You've seen this equation. It's the Schrodinger equation. But look, there's a t in there. There's no x's. So this treats space and time differently from the start. I don't think that is necessarily incompatible. Well, I know for a fact it's not necessarily incompatible with Lorentz invariance or diffeomorphism invariance, because this equation works perfectly well with quantum electrodynamics or the standard model, right? You've chosen a time parameter, but you could have chosen other time parameters. That's the way that Lorentz invariance shows up. But but Lorentz invariance or diffeomorphism invariance are not built in from the start in this approach. You need to find a Hamiltonian, or at least you need to assume there is a Hamiltonian where those features do emerge. You could try to be more clever and say, well, I'm going to start with a more a priori, I'm going to level the distinction between space and time from the start by doing something like the Wheeler-DeWitt equation, where h psi equals 0, right? But if that's your starting point, and that's your only starting point, this whole program is completely impossible, because there are no energy eigenvalues to work with. You're in the 0 energy eigenvalue state. There's nothing to do. So you need some data from which you build up everything else. And here, the data that we have are the eigenvalues of the Hamiltonian. Can you get different topologies and geometries and so forth? Sure. In principle, you can. But again, that's all put into the Hilbert space and the state and the Hamiltonian, right? I mean, it's things you could get in different ways, but it depends on your choice of Hamiltonian, which reminds me of the question about why this Hamiltonian, right? Like, why do we have a Hamiltonian where there are local interactions or Lorentz invariance or anything? There's a separate discourse. I forgot that it was not, I thought it was going to be my slides, but there is an upcoming paper where I talk about this. And here's the interesting thing. When you believe in many worlds, when you believe in the Everettian interpretation of quantum mechanics, you start with a state, you let it evolve, all of the physics are contained in the Schrodinger equation, right? So the only thing that ever happens is you branch the wave function, and that's what you interpret ex post facto as quantum measurements and so forth. And the branching means that you have the world in which you live is defined by a certain superposition of states, of energy eigenstates, for example, and that will be a slightly different superposition in different branches. Every branch is a slightly different superposition of energy eigenstates. And maybe over time, it can become a very different superposition, so that one classical branch of your wave function might involve completely different energy eigenstates than a different classical branch of your wave function, right? If that's true, so Jackie Laudman and I wrote a paper about energy conservation that makes this point. And so if that's true, and you also believe that the effective local laws of physics are simply reflections of what the energy eigenvalues are, then what that means is that as time goes on and you branch, different branches can see different effective local laws of physics. And what that means is that maybe you start with a Hamiltonian where there isn't locality or Lorentz invariance or whatever, but there's some dynamical process according to which the branches on which classical physics happen emerge through the Schrodinger evolution. So maybe there is some dynamical reason why the universe that we live in is so well approximated by a local Hamiltonian with things like Lorentz invariance. That is complete speculation at this point, but it is very, very interesting as a direction to move in.
Okay, but so you don't have an explicit idea how to later install the diffeomorphism invariance. You think it will emerge in your picture automatically? Okay.
Yeah, just like the three-dimensionality of space, that's completely dependent on what Hamiltonian you use. Same thing.
Yeah, of course, that's okay. Yeah, right. Okay, thanks.
Okay, so Gaetano, go ahead.
Okay, very interesting talk. Thank you, and thanks to Cohl. I want to ask some clarification. As far as I understand, when you have introduced your modular Hamiltonian, you have assumed that the time may become also complex. So in particular, you can take an imaginary time, and so it's proportional to the inverse of the temperature. Is it correct?
I mean, all those words go
Because you
well beyond any
didn't show, you took just the exponential of the Hamiltonian without any factor in front of the Hamiltonian.
That's right.
Yeah.
So there's I'm just setting the temperature equal to 1 because I'm not letting it evolve or coupling it to a heat bath or anything like that. It's just a normalization constant for me.
Yeah, but so you are assuming that you are doing equilibrium. You are in equilibrium situation.
No, I don't need to do that because again, it's not really a thermal state. It's just defining the Hamiltonian with respect to which whatever density matrix you have would look like a thermal state.
Anyway, it makes a difference whether it's real or imaginary. The factor in the exponential.
Yeah, it's real. It's real. And what I'm doing, it's real. It's a real number.
So, okay. So, and then I think it should be some sort of equilibrium thermodynamics. Anyway, the result will, your Hamiltonian is very similar to, I mean, something like Ising model and so on. And so you might expect that there might be phase transitions depending on the value of this inverse temperature. that can make a lot of differences in your phenomenology. So
yeah, look, sure.
An observation. So have you any expectation what would change with the different values of the beta of the inverse temperature?
Well, there's no, I mean, roughly speaking, no. I'm allowed to choose it to be 1. So I can't really vary it. It's just a normalization. But it's not like an Ising model, really. I know why you think it looks like that, because it is sort of nearest neighbor interactions, et cetera. But it's not on a lattice. It's on a flexible kind of space-time in which we're defining the distances ex post facto from entanglement, and that actually does make a difference.
Yeah, but it might have a phase transition. I mean, yeah, you might expect. Yeah. Okay. But anyway.
Well, again, we're imagining there's a Hamiltonian, and of course there will be an interpretation of, you can always just say, given a Hamiltonian, that you're in the ground state, right? And it doesn't sound like any information. If you have the Hamiltonian and the ground state and a factorization, then you can start telling stories about what the state looks like in that factorization, like what the entanglement is, what the phase transitions might be if you change the state to something else. But everything we're doing is very, very close to the ground state of this Hamiltonian. Not exactly, we perturb around it, but that's our starting point.
I see. Okay, thank you.
Okay, thank you, Gaetano. So B. Hens, oh, actually he disappeared. So there was somebody that had a question, and I don't know if they're going to come back up or not. Okay, looks like Torsten has another question. Go ahead. Every time it takes 2 tries. Except now it's not letting me on here. There we go. Okay, go ahead, Torsten.
Okay. I have a question again. Sorry. The question is, what did you expect happens with your tensor networks for the large curvature, like going into? Currently, you are looking for more semi-classic, or for not for small gravity contribution, but for strong gravity. Did you think it's degenerate to the tensor network into maybe like a tree or like a dimensional reduction, or what did you expect for really large curvature? Or did you think it keeps connected in a level, keep entangled?
I have very few respectable thoughts about that, except that it won't be the same structure at all, I think. I mean, we're not starting with the decomposition, right? We're starting with just vectors in Hilbert space.
Yeah, I understand, right.
So I think if you look at states that are very far away from the vacuum state, the decomposition itself will change. And so that's very interesting, but I don't know how it will happen.
Okay, thanks.
Okay, so, oops. So B. Hens, go ahead.
Yeah, that's a strange acronym, but I didn't choose it. It's very brief. Are you aware of the ideas of the German physicist Carl Friedrich von Weizsäcker? He had similar ideas to yours already in the 1950s. So he wanted to start with from Hilbert space and develop all of field theory and gravity, just starting from, well, the simplest 2-dimensional Hilbert space and build everything out of it.
No, I mean, I know von Weizsäcker, but I did not know that he did things like that. I will have to look that up. That's interesting.
Okay, I can thank you. Yeah.
I mean, I've often said there's no reason this couldn't have been done in the 1950s. So that maybe somebody did. I don't know about it.
They had some trouble later, but they tried. Okay, that's it. So.
Great.
Okay, last chance. Does anybody else have any more questions? No. Well, thank you so much, Sean, for such a wonderful talk.
Thanks for having me, Nicole. It was great to be here. Yeah.
Oh, yeah, my pleasure. Thanks to everybody for your questions. And so I should mention that Sean's colloquium was our last seminar for the session before we're going to take a bit of a break. So I just want to say thanks to everybody again for showing up so consistently over the last 7 months. and for having a love of this subject that has made organizing these seminars a worthwhile endeavor. So I hope to see everybody again for a second round.
Bye-bye. Thanks, everyone.
Thanks.